Hello everyone, welcome to lecture number 12. Today's topic is push notifications. Last time we did a basic architecture example looking at the National Gun Violence Memorial as a case study. This website is actually in some sense similar to Wikipedia because you can think of it as an article publishing system. And as a result, the architecture we had was the same kind of basic three-tiered architecture. So on the front end, we had a caching layer with a content delivery network. We had load balancers. Behind that, in the middle tier, we had a stateless application. And this is where the bulk of the custom code is. On the back end, there was a SQL relational database with read replication for scaling. Also on the back end, we had an S3 file store, which is used to store the large media files that wouldn't really make sense to be stored in a relational database. And I guess that was maybe the most new part of that architecture compared to other things we've seen. In this case, we're using the S3 for photos. That's a pretty typical use case for S3. So this design scales just like Wikipedia does, but the reason why we're able to achieve that scaling with a simple design is because the majority of traffic is reads rather than writes, and there's not a lot of interaction between users. There are several different examples. Later on in the class, we'll learn enough to talk about other kinds of architectures that are more complex to handle more difficult scaling problems. So today, again, the topic is push notifications, and this is going to be the first time that we're breaking down the client-server architecture. So everything we've talked about so far is kind of a client-server design, where there's a client and a server, and actually a lot of the interactions we've talked about have been HTTP interactions. HTTP specifically is a client-server protocol. There are two roles in every HTTP interaction. There's a client and there's a server, and you know, usually the client is a web browser, but it could be a smartphone app or a desktop app. The client is making a request, and the server's role is to give a response. Now, that's the most common kind of architecture, but it's not the only kind. Today, we're going to be talking about other ways of interaction. So specifically, we're going to talk about times when the server needs to send a request to a client. And that's kind of a breakdown of the terminology, because when we call things a client and a server, by definition, we're kind of we're structuring that definition of roles in such a way that we expect the client to make requests. In other words, the interactions start with the client. So for example, if a person clicks a link in a web page or clicks a button in an app, that software will send a request very often to some kind of server. That's the user doing something first. The reason why that interaction between two machines happened was because something happened in the client. Sometimes it's due to a user, or sometimes it's programmatic, like you could have JavaScript running in a browser, or native code running on, let's say, an iOS application that periodically does something and sends a request, a REST request, typically. In that case, the client is starting that interaction, and the server is responding. Okay, but that doesn't fit every use case. There's some situations where we want the server to start an interaction, something that we would think of previously in a traditional design as a server. In other words, the machine that's running in the cloud and that's listening for requests that's always on. Can you think of any situations where the server should start an interaction with a client? In other words, and I'm abusing the terminology here, so when I say server, I mean the machine running in the cloud that's always on, and by client, I mean, let's say, a smartphone app or a web page running on your laptop, or an app running on your laptop. In what situations would the server start an interaction? In other words, the client did nothing, but got some kind of like a message from the server, or got a request from the server more generally. What do you think are some examples? Stop and think about that. Well, I have a few examples for you. So the first one is a messaging app, right? So if we're using WhatsApp, and we send the message to our friend, that interaction is started by one friend, but it causes the other friend to receive a message. So the server, when it gets that new message, it has to deliver the message to some other user. So in that sense, the server is starting an interaction with the second user. Similarly, if we are using a ride-hailing app like Uber, a customer and a driver has arrived to pick up a customer. At that point, you want the customer to get a alert on their phone so they know what's happening. There's some kind of event that's generated in the system, probably triggered by another user's app, noticing that it was in the geographic region of the pickup. That tells the server that, and the server tells the customer that their driver's here, right? Another example is with eBay, an auction site. If a user placed a bid on an auction and they were outbid, that means someone else placed a bid that was higher than them. So it's another user doing something that causes you to want the service to want to send a notification to someone else. But I have a fourth case here, which doesn't really relate to any users doing anything, but is more related to just a timeout or an event generated entirely by the system. So, for example, if an eBay user wins an auction, in other words, the auction ends and they're the highest bidder, that's just based on time elapsing. No one really did anything at that moment. I mean, a long time ago, maybe you placed the bid, which ended up winning, but at some point in time, the server notices that auction is ended and it needs to send a message to the user. Okay, so these are all different kinds of interactions that start with a server and go to a client. Although the first three were interactions that involved two users, and one user started the interaction, it went to the server, and the server had to notify a second user. Okay, but in some sense, they're all the same, in that we want a server to be able to start an interaction with a client that didn't previously do anything. In all four of these cases, the user who was getting the notification or message or request wasn't doing anything at the time that that the message was needed to be delivered to them. They were idle, right? Okay, so in the earliest days of web services and online technology, email was the way to do this, and the only way to do it, really. And it's still used these days because it's kind of a simple way, an effective way to send notifications. If your notification is just like to tell someone that something happened, then you can send them an email. The way that you send an email is by using the Simple Mail Transport Protocol, SMTP. And in practice, you just need to connect to an SMTP server and have like an account on that SMTP server to log in and send messages. So every cloud provider provides some kind of SMTP service that you can pay for to relay messages to them. You also can use it directly by just implementing the SMTP protocol, but then it's hard to do that without getting your messages marked as spam. So technically any machine on the internet can just send email without having an account with anyone. They just can send it directly. But that's not recommended. So similar to that, nowadays we can also send text messages, SMS messages, programmatically by connecting to some kind of service like Twilio or SNS. So these are services that have APIs that allow you to programmatically generate text messages, right? Of course, you have to know the receiving person's phone number, just like if you're sending an email, you need to know the receiver's email address. Okay, fine. But those two both work. These are two mechanisms that work well for notifications. For many applications, it's good enough. And so we get something that's kind of like sending a request from a server to a client. It's not really a request in the full sense of the word, because we're not interacting directly with the app. Like, we can send an email that has a link to your app, and so the user getting it could click it to see it. Like, for example, if you win an auction, eBay can send you an email that says that you won that auction. It could have a link that you could click on to pay for the auction, but the user would have to actually click that link in order to start that activity. Whereas what we might want in many kinds of apps is something more integrated than that, where something actually happens immediately in the user interface of the application without us having to like click an email or click a link in an SMS. Okay. All right, so in some sense, we want to be able to reverse the roles of clients and servers and have these machines that are running in the cloud send messages to clients. But it's not so easy to do that as we might think. Like the mechanism we have for what in general we call these remote procedure calls, where we're kind of like invoking a function on another machine. The mechanism we have for that most commonly is a REST API. And so you might think that the client could implement a REST API that the server would call, right? So the server would send an HTTP request to the client. But this is difficult because clients, in the sense of like laptops and smartphones and desktop computers, these are not easily reachable from the cloud. And in that sense, I'm saying the internet is not a network of peers. Theoretically, the internet is a network of peers, but it's not in practice. And of course, the networking class goes into more detail. Why would a user, and I'm showing this picture as a hint, this is a mobile user from 1984 using an old style cell phone, right? If you imagine this is now in 2020s, this is a smartphone. This person's using an app. Why is it difficult in general to reach a mobile user or a client user, I guess, in general? There are actually many different reasons why this is difficult. So why don't you stop and think about that, see how many you can come up with. Okay, so first of all, there's mobility, which I'm hinting at with this photo, right? If the user moves around, they're moving around to different locations in the network, that means that their IP address changes. If you don't know about IP addresses, but just think about the fact that if you're moving around in a network, then to deliver messages to you, that somehow the network has to know where you are, and others have to know where you are in the network. The IP address is your location in the network. So as your IP address changes, anyone else who wants to send you a message over the network has to know your new IP address, your current IP address. Okay, so a smartphone user that's moving around may have different IP addresses as they move around. That's a problem, right? In addition, the IP addresses that you have very often are private, which is to say that they're NATed. Network address translation is what NAT means. So if you're on a home network connected to one of those like plastic Wi-Fi routers, or even if you're on a campus, whether it's a corporate campus or university campus, very often you won't have your own public IP address. Rather, you will be sharing a public IP address among your nearby users, other nearby users. Okay, so you don't have a public address, so the rest of the world actually can't contact you directly. They have to contact some kind of a NAT, have your message flow through a NAT device. I'm not going to go into details in this class. That's more of the topic of a networking class, but sharing IP addresses with these private addresses works well only if all the requests are starting from the inside going outward. It doesn't work in the reverse direction. Okay, and related to that is the fact that even if you do have a public IP address, your device might have a firewall, or the network might have a firewall that prevents requests from the outside from going in. Now, firewalls are kind of like hacks in some sense. Like they're not. The internet wasn't designed to have firewalls, but over time, network operators have found that it's helpful in general to their users if they do implement firewalls to prevent random requests from the outside from reaching the machines inside, because in general people tend to run software that has vulnerabilities, like old versions of operating systems, and developers write buggy code, yada yada yada. Okay, so firewalls are out there. I mean, and that prevents client machines from being contacted. Again, like the NAT devices, firewalls generally allow things to go in the flow in the outward direction, but not in the inward direction. And these are things that are not problems when you're operating a server in the cloud specifically for the purpose of handling requests, right? Finally, these clients that are laptops and smartphones or whatever, random people using services, they don't control their own DNS servers. You'll find when running a service, DNS is a way to make your IP address known to people. Even if you want to allow your IP address to change but still be reachable, you can use a host name, like let's say www.northwestern.edu. That's a host name that gets translated to an IP address through DNS, and the IP address could change fairly frequently, and that would still work if you had your own DNS server you were controlling. But users don't really have that control. They don't have their own DNS servers to manage. Okay. Finally, you might have also thought of these devices. The clients are using battery power. They're not on all the time, so your device might be off, or you may be out of radio contact as you move around. So the service can't rely on, even if it wants to deliver a message to you, the client device might not be available at that moment, and that really complicates things, because maybe you need to do some kind of retry or queuing, which is a pain to manage. So similar to that, even if your device is on, the app itself that's listening, the app that should get the message might not be running. Okay, so if you're using a smartphone, typically the smartphones only keep like a few apps running at any given time, and if you like hit the home button to leave an app and you don't use it within like a few minutes, then typically it'll be shut down because there's not a lot of memory on those devices, which is different than what happens on a laptop computer, on a desktop, Okay. All right, so for all those reasons, clients are difficult to reach, and for those reasons, we generally don't make them reachable. Instead, we just have the clients initiate requests themselves. So we tend to design services. The simplest way to design services is to assume that the client is always going to start any kind of action that needs to happen. So we have server actions that are synchronous with the client. Servers are well known, they don't move around, and so that works. That's the traditional design. It's not always sufficient, though, for all those situations I was talking about before, like notifying a user that their Uber driver is here, or notifying a user that their auction's about to end in 10 seconds and they should place a bid. You don't want to send them an email. Email's not good enough because they're not going to check their email necessarily fast enough to do the action you want them to do, which is to bid again. So push notifications are generally the solution. I misspelled that here, unfortunately. But push notifications are a series of hacks, I guess, and conventions for sending messages to clients to get around these problems that I've been talking about. Okay. All right, so in general, here's a high-level view of what a push notification service looks like for a smartphone. Okay, so what we're doing is creating an intermediary service. In this case, I'm showing the Apple push notification service. I'm showing a screenshot of an iPhone. But the same thing exists for Android with the Google Cloud Messaging service. Basically, we have all these apps, several apps, any number of apps that want to be able to send requests to clients. For all the reasons I mentioned before, they can't send messages directly to the client. The app might not be running, it's behind a firewall, it has a private IP address, blah, blah, blah. So instead, if they want to deliver a message to the app, they send it to the push notification service. This third party, they actually send it to Apple in the case of iPhone, and then Apple queues it up in some database or a message queue, depending on how you want to think about it, and it will deliver it. It'll try to deliver it immediately. If not, it might wait a while and deliver it when it can, or it might give up if it never can deliver it. It's not guaranteed to be delivered, but it'll make best effort. The phone that wants to be able to receive push notifications from any one of the apps that are installed, it makes a single outbound connection to the push notification service. So this is like a central meeting place kind of for the messages. The client makes a request. Outbound connections are allowed by the firewall. Outbound connections from the private internet to the public internet, or the private local network to the public internet are possible, not the reverse direction. So it makes an outbound connection, and it leaves this connection open. The way it leaves that connection open is by sending keep alive messages periodically. So there's some work involved in keeping this connection open, but it only has to do that work once for even if there are hundreds of apps installed on the phone that want to be able to send push notifications. So there's one set of central infrastructure. There's one connection from the client. If the client moves to a new IP address, it has to make a new connection. That work is done just once instead of for every single one of the many apps. Even if, let's say, Snapchat is not running on the phone because only the foreground app can be allowed to run at any given time. Even if Snapchat's not running, Snapchat can still send a message to Apple that will deliver it to the phone to show on the home screen so the user can click it and then launch the Snapchat app, for example. Okay, that in a nutshell is how push notifications work on smartphones. Okay, so one of the key ideas here is location registration. The phone, the device, whether it's iOS or Android, has to, whenever it gets a new IP address, in other words, whenever it turns on or moves to a new location, the operating system has to make a new connection to the push notification service. And that push notification service will store the user ID and the IP address in its database so that if any notifications come in, those notifications from the third-party services like WhatsApp and Snapchat, they will be identified by the user ID, not the IP address, because WhatsApp and Snapchat now don't have to worry about the particular IP address of the user because that's going to change over time. Instead, they'll just have this long-lived user ID or device ID or app ID, depending on the terminology you use, and the message. So they'll send this to the central Apple or Google push notification service. That service will know where to deliver it to because the phone as it's moving around is keeping that new connection. It's making that connection every single time it moves to a new location. So So the central notification service can make that delivery. Okay. Yeah. So one nuance here is, in order for this connection to be kept alive between the client and the push notification service through that NAT device, the OS has to keep sending keep alive messages maybe once every minute or so, but you only need to do that once for all the apps on your device to be able to use it, because as I showed here in this picture, this service is handling messages from all of your hundreds of apps through one connection from the cloud to the device, and the device keeps that connection open by sending one message every minute or so. Okay, cool. So there's another detail here to make this work, which is getting your apps. You have to have some way to give the apps the information they need to send a message to the push notification server that will allow it to make the delivery. In other words, the app, this is the same triangle that I was showing you before, so the locations are the same. It's a slightly different rendering, but think of this app server as like the WhatsApp or Snapchat. The push server up here is Apple or Google, and of course the device here is the user's device. There's a registration that has to happen first for this to work. So the app running on the device has to request a device ID or a user ID from the push server. That's what this first step is, registration. And this is the time when on your device you'll see a pop-up that asks the user, do you want to allow push notifications? If the user says yes, then the app through the OS will send a request to the push server to get an ID. Now this is app code running on the device that has been written custom by the application. So it could be the WhatsApp app or the Snapchat app in this case. Will then, in whatever way is appropriate, send that ID that it got that the app will generated. It will send that ID back to its cloud server, its backend service, and this will be stored in a database. That's step number 3. Because in the future, if WhatsApp is going to want to know that ID so that it can send a notification through the push server that will be delivered. So much later on, eventually that user gets a notification because someone sent them a message, days later. The backend knows that new message was created by some other user. It needs to deliver it to a user. It checks its database to see whether at some previous stage the app, some app for that user gave it a device ID. If it did, then it can send a message to the push notification server saying, okay, here's some payload. Payload is like the message that should be delivered to the app. Here's some payload and here's a device ID. Please deliver it to the user. The push server will use that device ID to recognize, to find the current connection that has been made by the app to the cloud, to the push service, and it'll send the message that way. Okay. So it's a several stage process, all designed to get this third-party kind of intermediary, the shared push server, to deliver messages for you because it's a lot more efficient. And because your apps don't run constantly when they're running on a smartphone. That's another key thing here. Whereas the operating system itself can manage the connection to the push server in the background. Notice that in this interaction we have the apps code running in 2 places. So that if we're talking about WhatsApp as an example, this app server is WhatsApp. The app running on the device is also WhatsApp, although it's interacting with the operating system. It's written by Apple. And this third-party push server here is the Apple push server. Okay. All right, so that was for smartphones. We also have push notifications on web browsers. Now, the normal way of using a web browser, the way web browsers were originally designed, and most of the times the way they're used, involves the browser pulling data from a server by making a request. So the server implements, let's say, a REST API. The browser makes a REST request to fetch data if it's happening in JavaScript, or it could be just like an HTTP GET request if it's due to clicking a link and navigating to a new page. Okay. But many modern applications also want to have some kind of pushed updates from the service. So for example, if you're using Gmail in a web browser, you don't want to have to click refresh to see the new messages. And also, even without the clicking, you don't want the software, the JavaScript running in the browser, to have to essentially like refresh automatically to pull, in other words. I mean, in the old days, that would be how you'd implement it as a simplest solution. Like the Gmail JavaScript that's running in the browser could every 10 seconds make a request to the server to ask for new messages. That is workable, but it's a hack, okay? Because you end up having a trade-off between either making requests really frequently, like every 1 second, and wasting a lot of effort and resources, or you make them less often, like once every minute, and like, okay, maybe the overhead isn't great, but then the user experience is poor because you have to wait a long time. You wait a long time on average before seeing your new message appear, right? So rather than have that trade-off, you'd want to have true push notifications, where whenever a message is delivered to the server, it immediately pushes a notification, an update to the client, right? Same as before, same as what we were talking with smartphones, but there's a slightly different set of technologies here, but still based around the same idea. We have fewer limitations here because like the web browser is always running. If you're using a browser tab, like it's there, we're assuming it's there, and we're not, So what we typically do with web browsers is use WebSockets. So your JavaScript code creates a connection to a backend, and that's long-lived, and it can accept messages that are sent backward. There's another solution called long polling, which was developed earlier. But it's kind of the same idea where you have a long-lived connection, but the long-lived connection is hacked through an HTTP GET request where the response is delayed. So like with long polling, you make a request to the backend, and the backend, like you basically ask, do I have any messages? And the backend doesn't just say, no, you don't. But if you don't have messages, it waits until you do have a message, and then it gives you the response. Or it times out after like 30 seconds. So after 30 seconds, it would say, no, you don't have any messages. And then your JavaScript code would immediately make another request, and it'd say, okay, now do I have new messages? And again, it would wait another 30 seconds before the response if there are no messages. If there was a message that arrived within that window while your request was out, then that would trigger the server to give a response early instead of timing out after 30 seconds. So you'd get that response immediately as soon as the data was available. Okay, that's what long polling is. Regardless of whether we're using WebSockets or long polling, though, we have the same basic architecture where the client has a persistent connection to one server, and that's where the requests come in. And also notice that's similar to the smartphone push notification service, except with browsers we're connecting directly to the service rather than to a third party, like in this case, in the case of smartphones, is Apple or Google. Okay. Yeah, so like I mentioned, WebSockets are long-lived bidirectional network connections. It's similar to TCP, if you've heard of that from networking class, but it's available to JavaScript in a browser. Okay, so you set up the connection, and then you can send JSON messages back and forth at any time between the client and server. And in this case, it's no longer really client and server, but they're peers. Like either one of them can send data at any time. The connection remains open even after the message was delivered, unless either side decides to close the connection. Okay, so that allows you to do push notifications. Oh, sorry, I guess I have a slide for the old style long polling, also called Comet. Just to explain that one more time, the client makes their GET request, and it'll wait for up to a long amount of time, let's say 60 seconds, before the server times out, and immediately it sends another request. But if at some point the server does have a new message, a new event, it will give a response immediately after that event was generated. So, and that would be a 200 response that has the data. The client would then make another request. So you keep polling, you keep making requests, and the server returns from the response whenever data is available, or after a certain amount of time it times out. Okay. Cool. This slide shows a comparison between, on the left-hand side, when it says HTTP, it's referring to the traditional client-server architecture versus WebSockets for push notifications. So we can think of HTTP as being half duplex, meaning that data only flows in one direction. Although that's kind of a weird way of thinking of it. But the messaging pattern for HTTP is request-response versus WebSockets being bidirectional. Push notifications are a core feature of WebSockets, whereas with HTTP you can kind of hack it with polling or long polling. And But one of the benefits of using HTTP is you get caching, you get CDNs and stuff like that automatically. Whereas for WebSockets, it doesn't really make sense to. There's no way to like automatically add caching in a way that works well and makes sense. Okay. Now, fundamentally, with these push notification designs or architectures, we have a fundamental challenge, regardless of which one we're talking about, of finding the one long-lived connection to the client. Okay, this is you kind of need to know a little bit about networking to understand this fully, but at a high level, if you have a network connection, which is called a socket, that's tied to one IP address. So when a client connects to the cloud for its push notification connection, that is connected to one machine in the cloud, right? One IP address in the cloud. So if the server wants to generate a notification, you imagine some large distributed system, like Uber, involves a lot of IP addresses in the cloud, lots of machines and whatnot. For the notification to get to me, it needs to not just be generated by the server. It's not enough that I'm connected to the cloud, but the message has to come to me through that connection that I already have. So we have to route the message from the origin in the cloud to that one appropriate notification server instance that the client is currently connected to. Okay, so to solve this problem, notifications are often a separate microservice, and actually what we saw with Apple Push Notification Service and Google Cloud Messaging was basically a separate microservice that was operated by a third party for this purpose. Okay, I have this hand-drawn picture of how you'd have a notification service, what role that would play in your system. So here there are two services that I'm running. So like I have my other services down here. I just have one like box here for that. This could be more than one though. And I have a set of notification servers that are load balanced. Okay, so this like middle tier here, these are the push notification servers. And the only purpose these have is for delivering messages to my clients. And I'm showing two kinds of clients. So there's this Game Boy looking thing is actually a smartphone. And then I have the web browser clients on like a laptop. And so what I want to be able to do is deliver a message to users regardless of what device they're on. So let's say I'm Facebook. I want to deliver Facebook notifications both to the app and also to the browser. Okay, and this notification service, microservice, takes care of that automatically by being capable of delivering messages in multiple ways, whether it's through Apple Push Notification Server or Google Cloud Messaging for the smartphones, or directly through WebSockets to clients, or perhaps through long polling connections directly to clients. And this push database has a record of what the different appropriate mechanism is to reach all the different users. Okay, you can imagine this service having a simple API where you make a HTTP post request with the user ID plus and then you have JSON notification body which will be delivered in whatever way is appropriate for that particular user. Because a user might have just a smartphone, like they might have an Apple phone, an iPhone. They might have just a web browser tab. They might have both, and you can deliver that same message to either one of them if your push notification service is designed to support that. Okay, so what this notification service does is it sees the user ID and looks up in the database to see what connection it might have, what options it has for delivering those messages. Like in other words, has a smartphone from that user registered? If so, is it Apple or Google? If so, what is the device ID? With that information, it can send the request to either one of those for it to be delivered. Or if it's a browser tab, what IP address is it connected to, both on the remote side and the local side? Because you might have to route the request to another device. Like let's say you send a notification to user Steve. That notification goes in here. This checks the database, sees that user Steve has a browser tab connected to this other fifth instance of the service. So the service sends a request over to here for that message to be delivered up here. Okay. To make this a little bit more concrete, I'm showing an example of what that push notification database might look like. So I have a list of users. For every user, I have an entry that each entry or each row describes a way of sending a push notification. So the user Alice has one way of receiving push notifications, which is an Android phone through Google Cloud Messenger, or Google Cloud Messaging, I should say, that's what it's called. And that user Alice has a certain device ID. Now remember, this was generated by Google and sent back to the app, and the app relayed it back to us, and we stored it here for future use. Okay, so then if we want to send a notification to Alice, we send a message to Google Cloud Messaging with this device ID along with the message it wants to be delivered. In the case of Steve, if I want to send a message to Steve, I have three choices. There are two web browser tabs, and there's one iPhone that's registered. For the browser tabs, notice I have three different pieces of information. I have the server that the tab is connected to, I have the client, and I have the port of the client, which you actually would need to distinguish to know which of the many connections that might be made from the client to the cloud you should use to send the message. Okay, that's a detail from the networking class that you might not fully understand if you haven't taken that. Okay, cool. Now, there are kind of off-the-shelf services to help you handle this. With AWS, the API Gateway supports WebSockets, and this can be integrated with Lambda functions, which are serverless functions. We'll talk about these more later on the class, to send messages through WebSockets. So the WebSockets are long-lived. Those are persistently connected to this thing called the API Gateway, and then your code on the back end can handle messages when they come in, and then send responses that are routed to the correct connection using a connection ID that's stored in a database. When the WebSocket from the user makes a connection, it stores the connection ID, and yeah, that's the way of doing it. But I guess this is just a really quick view of it that you can look more into on your own if you're interested. All right. So to recap today's discussion of push notifications, we started with the traditional web design that uses a client-server architecture where the client is always making the requests. But sometimes we want to flip that around and actually push data out to clients instead of the client always pulling. That's difficult to do for a variety of reasons. And we solve it in two different ways which are related. With mobile operating systems, we have special push notification services we have to use that handle this for us. The reason why these exist is because it allows your app basically to receive a message. You wouldn't be able to deliver push notifications to smartphone apps if this didn't exist, because your apps aren't running all the time. Okay, so the OS has to manage it. It allows you to have a single connection from the phone that's shared by all the apps, so it makes it efficient for a phone to be able to receive notifications from hundreds of apps. It allows the app the notification to be delivered even if the app isn't running. You can do that kind of like badging or banner notification that's controlled by the OS. On web browsers, we can use WebSockets or long polling to implement push notifications so we can update the UI immediately. In both of these cases, the complication is that your client's actually connected to one machine on the back end, and your service has to somehow relay the message from that one connection to the client. So you end up building a database on your side to store information about which clients are connected to what machines. All right, hope that made sense. See you later.